Okay guys, so in this video we're going to be talking about wires, or our wire elements for our hex beam. And I find this quite an interesting subject because we build this quite elaborate structure and it's purely there to support these wires. Either it could be one wire, it could be 6 wires, just depending on how many bands that you've got. So before we get into the wires and look at what I'm actually using, once again we just want to do a little bit of theory. So I'm going to actually just try and draw 6. These would be the spreaders. And like that, they won't be the perfect equal length, but hopefully you're going to get the just. So imagine this is our spreaders, and then we need to do something like this. So this would be our reflector. Okay, like so. And then we need to have a director. So we're going to put that in blue, like this. And this actually runs down. And it actually splits in the middle because that's our feed. And it runs down like that. Now this is actually, so this is the hex beam elements. So I've changed the colours here. So we've got these little gaps. That's probably not the best colour. Let's use green for that. So we've got, these are we call K4KIO calls these the tip spacers, and I like to call these that as well. It just keeps the naming the same. So we've got a reflector, we've got a director, and we've got a spacing. Now, that spacing is very, very critical, so that spacing never actually changes. Again, this is our feed point in the middle, where we connect our wires up. So this is one half of the dipole, and this is the other half of the dipole, which is just slightly bigger. Okay, so that's our basic element. Now, if we actually just draw this out, how the finished thing would be, I think it would be something like, so that'd be like that. And imagine if we had this laid out straight, we would have a tip spacer, and then we would have our reflector. Obviously this is not to scale, this is the reflector, which is longer. We would have our tip spacer, and on the end we would have our other driven element, something like so. And right at the end of these, you need to then put a little ring connector or something, here like that, here like that, and that's our hex beam element. Okay, so that's hopefully that's made some sense by just making a little drawing. I'll just get rid of this. I can get rid of this now. Okay. So building my hex beams, this is actually one of the working documents that I actually used. I got this, I can't remember, so I apologise who I'm not crediting with this. I think it could be K4KIO. Now, just that's exactly what I've shown you there. So I made them exactly to K4KIO's plan, but I used a slightly different wire, which I'll get to in a minute. But Leo gives you a number of wires, whether it's insulated or uninsulated, because that affects the velocity factor. And you need to take that into account. But don't be surprised if you're using a wire that's not on that list, like I did, that you will have to make changes manually. Now, the wire in question that I'm using is this stainless steel. And I know a lot of people say do not use stainless steel, but I think it's got a lot of advantages. And the minor disadvantage is that it's maybe possibly slightly less conductive, that I don't think you'll ever notice on air. Steve, G3TXQ, he said he did model this. I was reading, and he did say the gain was slightly down on this, but I'm not going to let that bother me. This is 1mm, 49 strands, so seven strands of 7. It's extremely flexible. It does not have any memory. It's really light, and that's why I actually like to use it. And I've made my hex beam elements up with this, and they fit because they're very small diameter, they fit nicely on this reel, and they happen to be really strong, but you don't need a lot of strength. Any sort of copper wire, PVC wire will actually do. Now on the ends here, you can see that we've got a bit of heat shrink, and that's to stop me actually getting jagged, because these wires are extremely thin, extremely sharp, and they will go right into your fingers. Okay, so there's little loops on here, and these just go onto between 2 washers, and I just tighten them up. So instead of using a ring connector, I'm just using the wire itself. It keeps things a lot simpler. In order to put a loop, I've got a little ferrule, copper ferrule. So if you're using stainless steel wire, you use a copper one. And I think if you're using the galvanized wire, which you wouldn't use, then it would be aluminium you use. So that's our ferrule on there. And I just take our crimp tool, like so. This is not actually the right one I have, but it's not the right crimping tool. But I just do that and it crimps it. And that isn't going anywhere. Alright, now I like to cut these a bit closer, but you can see that these are starting to fray at the end, so I would nip that closer and then I would put the bit heat shrink over there, because I've learned through experience that if you don't, you'll get a painful one. And if you do that, you won't actually have any problems. Now, we've got these little tip spacers that are in here, and these lengths are actually critical. Again, you'll get these from the table on Leo's website or in the bill of materials linked below. So that's an Excel sheet, and if you look at the tab along the bottom, you'll see that I've put wires on for this wire that I'm using here, and I've also put in the sizes of the tip spacers, so you can work to those if you so wish. So for the tip spacer string, I'm using this Mastrand P. This is the same braided rope that I used for the rope supports. That's got about a 90 kilogram breaking strain. So what is that? That's like 200 pounds or something. We're never going to put that much strain, and these are used on commercial hex beams as well. It's really thin, it's really light, but again, to keep things neat, I'm using a ferrule, and this is an aluminium ferrule, and I got these from eBay of all places, really nice and cheap. And once again, what you do, or what I was doing was, we actually take a length. So I was using a marker actually. So say this plan here was 305 millimeters. So you would basically measure 305 to here, between here and these points. And at these points is where you fold it over. So these need to be really accurate, okay guys? So make sure you get them probably within 1/4 inch, 6 mil. And then, so the end of the dimension would be here. And once again, I just get my crimpers like so, and I just crimp them together. All right, and you just do the same on the other end. And when you cut this, you will need to use a lighter. I just use the flame of my soldering iron to fray it over and then let it cool, and I just rub it with my fingers, and that stops it from fraying any further. And then really then the job is a good one. Now, I spoke about wire choice here, and that I'm using this stainless steel wire, but I do have some other wire here, because you can decide what you want to use. This cable here, this is a very inexpensive cable. I think it's 0.75 millimeter. It's PVC coated. I think they call this, I can't remember what they call this, but standard electrician's wire. It's okay. It's fine for general antennas. It's about £20 UK pounds a reel, so $25 or so for 100 meters, 300 feet. It won't be as much as that, will it? Yeah, it will be. Yeah, that's about three and a bit to 1. And yeah, I use this generally. I use it for verticals because it's really cheap, and if I need to throw a bit away or lose a bit, then it really doesn't bother me that much. So this is one option that you could use, but what you find is in cold weather, it really does get stiff, and that's the only thing that I don't like about this wire. If you want to go upgrade a little bit more, this is DX Commander DX10, and this wire is so much more flexible and supple than the standard PVC wire. And what I also like about it, there is a diameter difference as well. It's actually thinner than this, because this really has a thick PVC jacket. So again, the wires are the same, I believe, the same number of wires, and they're the same thickness. So, you know, in terms of use, they'll be absolutely fine. So this wire is probably going to be the wire that I'm going to use going forward for my next hex beam, which is probably going to be the city beam, which is the 15/6 version. And I have a different center post that I'm actually working on, so you know, stay tuned for that. So that's a couple of options that you can actually use, but you know, you can do any which way to suit. Now, if you find that when you set up your wires, the hex beam elements, and you get up there and you find that your SWR just isn't quite right, you may need to make adjustments. And Leo, again, K4KIO, he actually shows you how to make this, how to make adjustments, or tells you how to do the calculation, because there's an inverse relation between the length and the frequency and percentage. So, which I'm going to do a little calculation here. I'll show you how I do it. It's been a few weeks since I've done this, so bear with me. But I've done this calculation before. So you basically see where the antenna is, or where the low SWR is, resonance point, whatever, and then you need to calculate the difference. So when I first set up the Hexbeam, it was, I think I needed to shorten the wires. Yes, it was much too resonant lower down, so I needed to cut the wires to bring them in. It just so happens that I had enough wire on them that I could do that, but you may need to make new elements. They may not just be enough to cut, but these, you know, this is one way of doing that. So let's take 20 meters for an exact 20 meters to the 14 megahertz band. So say say your lowest point SWR is 13.9 megahertz, right? But you want it to be 14.175. That's the middle of the band, isn't it? Okay, so that's actual. That's the target. Okay, so quite simply you can do it one way or another, but I just divide one by another. So I just say, we'll miss out the point, so hopefully you can see this. So I would just go 13900, and then I would divide that by 14175 equals, so, and I'm going to take away 1 equals, so this is 1.9% difference in frequency. And that's the value that we need, all right? So let's just write that up here, 1.9%. So we've done that calculation. So you would have to do this for each band, okay? So say our actual length on one, I'm going to use this example here, okay? So I can look at that and take you through it. So look at the reflector, which is the big long wire. So my actual length, so you need to measure what it is currently when it's at the wrong frequency. So say the length was 5.223 millimeters. I'm a metric guy, so you need to do it in inches if you want, but I like metric here. So that's the actual length of the reflector. Okay. Now we want to make that 1.9% smaller. All right. So there's a couple of ways that you can do it, all right? So you could do 5223, and then you say you could divide that by 100, which gives you 1%, and then you could multiply that by 1.9, all right? And that gives you 99.237, 99.237 millimeters. I'm not going to worry about that. And I would take that to, I would just round that up and go to 100 millimeter or 4 inch. So that's how you would do the calculation. You can put it in an Excel. That's how I do it. There's probably easier and quicker ways to do the maths. But that's how you would make the sizes. So you would then take 100 millimeters from this. So then you would go to the plan. That 5223 would then go to 5123. So you would then change the size. Now you need to do it for all the elements. So you need to do it for this one, and then these two would be the same size. These are identical. So you need to keep everything that size. Again, you need to keep your tip spacing the same. That doesn't change. And if you do that, you should be in the ballpark. Now, I did this with all my elements, and I did it at the same time. And if you actually look at these, you can see that I was 2.9% out on 10, 2.6 out on 15. They were all similar, 17, 2.3, 20 meters, 2.3. So it was all relatively out by a consistent figure, which was pretty good. Again, I was using this stainless steel wire. That's why we got that result. I went by Leo's calculations, but that was using the PVC coated copper, but I had to go with something, and I knew I was going to have to go through this exercise. Okay, so hopefully you don't need to do that. You can just go through the table on Leo's website, but if you need to do the calculations, you can do it now. Slight word of warning: when I made the calculations, in theory every SWR should have been exactly where I wanted it, but it wasn't. It was slightly higher now, so the wires needed to be slightly longer. And I thought, and actually instead of doing 2.9, it should have only been something like 2.4. I found out that these in real terms are about 0.4 to 0.5% out. And the only thing I could think of why that is because you have all the wires and they interact with each other. So that's just one of the downsides. So sometimes the theory doesn't always match the practice. So there we go, guys. Just a quick one on Hexbeam elements there. It's pretty open, you know, do what you want to do. Do it with materials that you have to hand. Again, I'm going to be using this stuff on my next Hexbeam, and this, yeah, it should work a treat. But I will need to go through this exercise again because the lengths will be different from using this wire. And then that'll obviously affect the rings round about the spreaders and how it's tensioned and so on. Okay guys, there we are, 73, all the best, and we'll catch you on the next one. Bye for now.